Okay. So last time we arrived at the following relationship for a structure stiffness matrix. Okay. So something we called KFF. Remember, right? This is a structure stiffness matrix connecting three DOFs. Right? So hence the subscript FF. And we arrived at the following equation, that the structure stiffness matrix in some sense equals to the sum of individual element stiffness matrices. E equals 1 to NEL, right? NEL is the number of structural elements in your structural system. And then you take each individual element matrix, and you know how to construct those. For truss elements, we covered those extensively. And hit it on the left and right by the ABF, our Boolean friends. E and ABF E transpose. Okay. So this is a structure, this is the element matrix. Okay. And sort of the takeaway message from here, right, is that structural stiffness matrix in some sense equals to the sum of element stiffness matrices. Okay, it's sort of an intuitive result, as you can imagine, but again derived from the various considerations in the earlier lectures. Okay, and so now theoretically this looks good. Okay. But imagine you solving a complicated structure, okay, with millions of trusses. I mean, think of some kind of scaffolding or a roof and the supporting structure for a large soccer football stadium, or think of a long span bridge, for example, where KFF would be order 10 to the 6 by 10 to the 6, million by a million. Okay. So the element matrix for the truss is fixed. It's 4 by 4 in 2D. In 3D is a little larger, but again, these numbers are something between order 1 and order 10, right? And so then, in order to get something of the same dimension, in principle, each one of those A's would be 10 to the 6 by 4, right? 4 by 10 to the 6, okay? And the number of elements would also be order 10 to the 6, okay? And so in order to construct the structural stiffness matrix, okay, you have to add 1 million times, right, a product of something that's a size 4 times 10 to the 6 by 4 by 4 and 4 times 10 to the 6. So you can see that something like this will take forever, even on sort of the more modern, faster computers. And so in order to do things efficiently, okay, somehow we need to get around the requirement of using A's, okay, and substitute something that accomplishes the same goal, okay, but without these explicit multiplications. Okay. And so we make an observation that right, ABF for element E, okay, is a matrix of zeros and ones, of, say, ones and zeros. Okay, so then you know that the product of something with zero is always a zero, right? So there's no way to really, build and compute these matrices. And another observation is that the ones lie on rows and columns of A, B, F, right, corresponding to the to the relation between element level, right, local, or element level, and global, or structure level, DOFs. Okay. Right. And then because you're either multiplying by 0 or by 1, right, what you see is that all you're doing is really, you're not scaling anything, right? You're essentially positioning the entries of, right, K sub B into their appropriate locations of KFF. Okay. And so then you can bypass the multiplication by ABFs by devising sort of the right algorithm where you start with the element stiffness matrix, you find their corresponding locations in the structure stiffness matrix and directly assign those values. Okay, so how do we proceed from here? Okay, well, let's go back to our example and let's look at element A. Well, delta 1, delta 2, delta 3, and delta 4 are our displacement degrees of freedom, right, for that element. Okay, if you recall, these were connected to node 2, these were connected to node 1, and node 2 had U1 and U2 as global or structural displacement degrees of freedom, and element 1 had U3 and U4. Okay, and so you also remember that U1, U2 were free DOFs, while U3 and U4 were restrained DOFs. Okay. Right. So then this introduces a structure that's called the ID array. Okay. And the ID array, okay, has two arguments, I and E. Okay, where E is the element number and I is the local DOF number. Right, so for every element number, every local DOF number, ID returns to you A, which is now the global DOF number. Okay. And so let's focus on element A, and let's try to construct ID array for element A. Okay. Right, you can see that local delta 1 corresponds to global U3. Okay, good. Right. So let's do ID for element A. Okay. Let's fill it up entry by entry. Right. Denote by the fact that this is element A. ID will change, of course, from element to element. It'll have 4 entries, right? Because I goes from 1 to 4. So 1, 2, 3, 4, right? This is our index I. Okay, and let's go to I equals to 1. I equals to 1 corresponds to delta 1, and delta 1 corresponds to global U3. So in location 1, we put a 3. We'll go back to this figure. We'll look at the next degree of freedom, which is delta 2. You can see that it corresponds to U4. So we'll put a 4 here. We go to delta 3, right? And you see that its global counterpart is U1. Okay, so whatever U1 is, delta 3 has to be, right? By compatibility. So we'll put a 1 here. Okay, and finally we visit the last element degree of freedom, which is delta 4. And what we find is its corresponding global degree of freedom is U2. So we put a 2. Okay? And so this is how we build up entry by entry the idea arrays. Okay? In addition, right, as before, because U3 and U4 are restrained, okay, it means that I know what the displacements are in this location. In this case, these happen to be 0. Sometimes you prescribe non-zero displacements, okay, such as in the case of support settlements and so forth. Right? So in that case, because there are no equations there, there's nothing to assemble, okay, there's not going to be a force vector, and these guys will not play a role in KFF, right, which only couples the free degrees of freedom. We're going to denote these entries by 0. Okay, no equations. 1 and 2 are free, so we retain those. Okay. So we zero out entries with no equations. Okay. Right. So now that we have the idea array, right, let's see how we use it. Okay. So use idea array, and this is important, in place of pre and post multiplication by ABF. Okay? And you would do this as follows. Okay, so let's look at element A. Okay? Let's look at the stiffness matrix for element A, and let me write it in the general way. It will be some entry K11, K12, K13, and K14. Okay? K21, K22, K23, K24, K31, K32, K33, and K34, and the last row, K41, K42, K43, and K44 of A. Okay? So in principle, it's a full 4x4 matrix. Some entries may be 0, depending on element orientation, but we keep it general. Okay? So this is our K, A. Okay? Next, what we'll do, I'm going to take the idea array I just computed, okay, and I'm going to put it on top, and I'm going to put it on the side of the matrix, 0, 0, 1, 2. Okay? This is ID of element A. Okay? So next thing we notice, right, the entries corresponding to IDs of 0, okay, row or column, will not contribute to the global stiffness matrix, as I said, right? KFF only couples free degrees of freedom, right? And so we can safely get rid of them. Okay? In our mind, we can cross it out. We can cross it out like this. Okay? So these entries will not participate in the direct stiffness assembly, which leaves us this block in the bottom. Okay? And then the rest of the idea array is used to position the entries of the local stiffness matrix into the global. Okay, which entries are given by the entries of the idea array. Okay, so let's visit K33. Right. Look at its ID value here and there is 1 and 1. Okay. So that means that whatever we had in KFF corresponding to 1, 1, okay, we're going to add K33A. Okay? Let's look at K34. Where does that go? Right? The row number is 1. The column number is 2 now. Okay? So KFF 1, 2 is whatever it had in it before plus K34A. Okay? look at K43, right? Now the row is 2, column is 1. Okay. So K21 FF is K21 FF, whatever was in it before, plus K43A. And finally, KFF22, right? You get the pattern. 4 goes into the global 2. So we take KFF22, whatever value was stored, we add A4, like this. Okay, right? And you see that this operation is much faster and much less expensive than trying to do the pre-multiplications by ABF. So this is sort of an amazingly efficient shortcut in how to handle things. Okay, all right. Now let's repeat the same exercise for element B. Okay, so we'll look at the element. Okay, recall it connects nodes 2 and 3. We had global degrees of freedom that are again U1 and U2, right? U5 and U6. And locally, it's still delta 1, delta 2, delta 3, and delta 4 like this. Okay? So then, what's the ID? All right. ID of element B equals 2. Okay. For element B, this is index I, 1, 2, 3, 4, has entries as before, right? And let's cycle through the local degrees of freedom and see where they point to, right? So whatever delta 1 is has to coincide with U5 for compatibility. So the first entry is 5 of the ID array. Whatever delta 2 is has to coincide with U6. This becomes 6. Whatever delta 3 is coincides with U1. Okay. And whatever delta 4 is coincides with U2. Okay. So this entry is 1, and this entry is 2. Okay. And then we do a final modification where we say, well, hang on a second, right? 5 and 6 are restrained. There are no equations there, so I'm going to place zeros here. Okay. And then I keep the free guys, which is 1 and 2. And so it so happens that ID for element B is exactly the same as the ID for element A. But again, pure coincidence. So what does this mean? Right? Okay, well, you go and you compute now the stiffness matrix for element B, okay, using the procedures that we derived and used in class. Okay. You arrive at an expression that looks like this. Okay. There'll be some K11B, K12B, K13B, K14B, K21B, K22B, K23B, K24B, right? K31B, K32B, K33B, K34B, and the final row is K41B, K42B, K43B, and finally K44B. Okay? So what's next, right? Then you just produced an ID array. Let's put it here. 1, 2. This is ID for element B. And we'll put it on the side as well. That's how we think about rows and columns in our mind. Okay? And as before, right? This row, this column, and this column, because the entries of the ID are 0, do not participate in the direct stiffness assembly. Okay? And so what remains is this bottom 2x2 block. Okay? And now let's see where each one of these go, right? We look at K33B, and we see that for the global structure, it corresponds to DOF1 and DOF1 for own column respectively. So we'll take whatever is in KFF11, right? and now add KB33 to it. Okay, this is done, handled, right? We'll go to K34, right? And the entries in KFF is 1, 2. So KFF 1, 2 equals to KFF 1, 2, whatever was in it, plus K34B. KFF 2, 1, right? Let's see. K43 points to row 2, column 1. So KFF 2, 1 equals KFF 2, 1 plus K43B. And finally, K44 goes into the 2 entry of the structure stiffness matrix. KFF 2, 2 equals to KFF 2, 2 plus KB 4, 4. Just like that. Okay. Again, only 4 sums are involved. Okay. Basically, four additions. Okay. As opposed to all these multiplications. Okay. And so then, from that example, we see, right, that your KFF, because there are only 2 elements, equals 2. Right, 2 by 2 matrix. And the first entry is K33A plus K33B. Right? 1, 2 entry becomes K34A plus K34B. 2, 1 entry equals K43A plus K43B. And the last one, right, the 2, 2 entry becomes K44A plus K44B. Okay. So what do you notice from here, right? If you recall, right, the structure of KE, right, you have the basic stiffness, K prime, for element E, right? Then this guy gets multiplied by gamma RBM. On the left, gamma RBM transpose, right? And then you get right? You get gamma ROT, right? And gamma ROT transpose like this, okay? All right, so let's look at the transpose of K. Equals 2, right? So how do you take a transpose? You have to take a product of 5 matrices, okay? And the way you apply transpose to the first one, you put it in the back. You apply transpose to the next one, you put it second. The third, you put it third, fourth, right? And so you find this becomes gamma ROT transpose, right? Followed by, right? Next is gamma RBM transpose, followed by K prime E transpose, followed by gamma RBM transpose, which makes it gamma RBM, and followed by gamma ROT transpose, which is gamma ROT. Okay. Now this guy is 1 by 1, so its transpose is the same as itself. Okay. If you look at this expression here, right, you see exactly that it's K sub E. Okay. So the element stiffness matrix is symmetric. Okay. And now right? If you look at the definition of KFF, right, either through the booleans or through the operations that we've developed, right? If you look at the off-diagonal entries, K34 makes it into the 1, 2, and K43 makes it into the 2, 1, right? Because the element stiffness matrix is symmetric, right? These two entries equal each other. Okay. Likewise, K34b and K43b, right, also equal each other. Okay. Which means that K12 in this case equals K21. So structure stiffness matrix is also symmetric. So if you have that kind of information, right, you can even skip assembling the lower triangular entries, okay, and just focus on the upper triangle. So you can save some more operations. Okay, let me stop here.